Okay, what I want to do is to show you an example of how to balance a redox reaction when the solution is basic. Sorry. When the solution is basic, how do I know the solution is basic? You look at KOH and you should recognize that as a base. I can tell you that if there is any ambiguity or vagueness, or there's not enough information in the equation to indicate whether it's acidic or basic, just solve for it as an acid, like I showed you in the Zoom meeting on Monday. But something as obvious as this is seeing KOH, that should tell you right away that it's a base. So the method for solving balancing equation redox reactions in a basic solution is the same as an acid, but there's an added step at the end. So I'm going to just go through and again describe how to balance equations. And then at the end, I'll show you that the extra step that's required. So the first thing we want to do is identify what is oxidized and what's reduced. If you've been working on the practice worksheet at all, you should be getting more familiar with how to spot the elements that you think are most likely the ones that are involved in the redox reaction. Right away, I see that on the reactant side, sulfur is by itself, but on the product side, sulfur is in a compound. So for sure, that is going to be part of the redox reaction. So I'm going to go ahead and assign oxidation numbers there. Sulfur is 0 on the left because it's a pure element. On the right-hand side, it's +4. So that is oxidation because it is increased in oxidation state. Then I'm going to go and look at chromium because I see that potassium is in ionic compounds both on the left and the right-hand side, which means it's going to be in its ion form, which means it's not going to change. And like I said, hydrogen and oxygen should be addressed last unless you see nothing else that is changing. So on the left-hand side, we've got dichromate. So I'm just going to, just to reiterate again, to make it easier to separate out the ion, to assign, oops, forgot the 2. If that makes it easier, then you don't have to worry about it. Or if you would rather, another way to do that is to include potassium. So potassium is +1, so that's a total of +2. Oxygen is -2, that's a total of -14. So what goes in the middle is what will make it 0, that's +12. But there are 2 chromium atoms, so you have to divide that over each, so that's +6. On the right-hand side, it's a bit easier because you have oxygen, which is -2, times 3 is -6. This has to be +6. There are 2 of them, so that's +3. And again, first checkpoint, making sure that one element in the reaction increases in oxidation state, like sulfur, from 0 to +4, and making sure that the other element that is changing is decreasing oxidation state, like chromium here is going from +6 to +3. That's reduction. So now I can write down my oxidation and reduction half reactions. My oxidation is sulfur going to SO2. SO2 is a covalent compound, so I cannot separate that. And reduction, here's where I would really, really recommend separating out an ion, especially because if you have, if you write K2Cr2O7 and then yields Cr2O3, you have no way of balancing the K. So that's another indication of when and how you can split ionic compounds, because if there's nothing else on the right-hand side that has K, then you think, oh, okay, well then I can just separate the K out. So I've got my dichromate ion, and this is why it was important in grade 10 to remember your polyatomic ions. If you cannot remember your polyatomic ions, I would highly recommend reviewing that. If you want, I can give you worksheets to help practice that. And on the right-hand side, I'm going to keep Cr2O3 together, just because I suspect that it is also a covalent compound. All right, now comes the balancing part, starting with oxidation. My sulfur is already balanced, so now I'm going to balance oxygen by adding the correct number of water molecules to the correct side of the equation. So I need 2 water molecules on the left-hand side, which means I need 4 hydrogen on the right-hand side now to balance charge. The charge on the left-hand side is 0. The charge on the right-hand side is +4. I need to make that 0, so I add 4 electrons. Now for reduction. Chromium is actually balanced. So both sides have 2 chromium, but my oxygen is not balanced. So I need to add 4 water molecules to the right-hand side for a total of 7 on the product side, matching the 7 on the left-hand side. Then I need to add 8 hydrogen on the left-hand side to balance with the 8 hydrogen on the right. And finally, I need to balance a charge. So charge on the right-hand side, again, is 0. On the left-hand side, we have +8 minus 2, which makes it +6. So I have to add 6 electrons. Now I have to ensure that both sides contain the same number of electrons because we have to lose the same number of electrons that we gain in reduction. So the lowest common multiple for 4 and 6 is 12. So I'm going to multiply oxidation times 3, and I'm going to multiply reduction times 2. Okay, so next step, multiplying oxidation times 3, I have 6 H2O plus 3S yields 3 SO2 plus 12 H plus 14 electrons. Boy, can you even add, bro? 12 electrons. Derp. Okay, my reduction multiplying out times 2, I've got 12 electrons plus 16 hydrogen plus 2 dichromate. That gives me 2 chromium 3 oxide, plus 8 H2O. Now, I want to cancel everything that occurs on both sides, starting with electrons, 12 each, okay? I have water on both sides, but I've got 8 on the right-hand side and 6 on the left-hand side. So all 6 of these go away. These 8 are reduced to, oh my gosh, what is my problem? Okay, fine, we'll do that. Here, 8 minus 6 is 2. Yeah. Okay, and then finally we have a hydrogen ion. There are 16 on the left and 12 on the right. So all 12 on the right go away and 16 is reduced to 4. Yay, I can math. All right, now I'm gonna write all of that out. I've got 3 sulfur plus 4 hydrogen plus 2 dichromate yields 3 sulfur dioxide plus 2 Cr2O3 plus 2 water. Now, coming back up here, again, we have to recreate everything, okay? Now, at this point, I guess it's kind of up to you what you want to do. This is where I would introduce the last step that you have to do before putting everything back together. Yeah, this would be the best place to do it. So the big difference between acidic and basic solutions, acidic solutions have a concentration of hydrogen ions in them, but basic solutions have a concentration of hydroxide. So because this is a basic solution because of KOH, we cannot have just hydrogen ions running around. So what we have to do at this point for a basic solution, here's the big difference. You have to add an equal number of hydroxide ions to both sides to neutralize that hydrogen, which means you're going to create water on the left-hand side, which means, yes, you'll have to cut that with the water that's on the right-hand side, but we do one thing at a time. So at this point, when you've balanced your half reactions, you've added them together, you've canceled things that occur on both sides, and you have your final, your not quite final redox reaction written. At this point, for a basic solution, if you have any hydrogen ions that are free in your equation, you have to neutralize them with hydroxide. I have 4 hydrogen, so I'm going to add 4. I'm going to add 4 hydroxide to both sides. Again, it's just like in math. If you do it to both sides, it doesn't count, or it counts evenly, whatever. All right, so now these two are going to come together to form 4 water. And that is going to delete the 2 water on the right-hand side, and it's going to cut this down to 2. So I'm going to rewrite where I'm at now and then go back to my main equation to try to put formulas back together. Okay, just do a squiggly to make sure that I know I'm on a new version of the equation. So I've got 3 sulfur plus 2 waters plus 2 dichromates yields 3 sulfur dioxide plus 2 Cr2O3 plus 4 hydroxide. Okay, now let's go back up to the main equation and see what we need to make one thing at a time. The first thing we need to make is potassium dichromate, K2Cr2O7. So I've got 2, WCr. You probably caught that, didn't you? I didn't see till just now. Okay, I've got 2 Cr2O7, so that coefficient doesn't change. So I've got 2 K2Cr2O7. I'm just recreating the same formula up here, and then I'm going to add however many potassiums that I needed to add to the right-hand side. So here I added 4K, 2 times 2. This is just a shortcut to what I was showing you in the solutions that I was doing. In the solutions, I was doing like all the steps, like adding all the ions to the left and all the ions to the right. But here's like, if you want to save yourself some time, you can just recreate the formula and add the necessary ions to the right-hand side. I find that easier. Okay, so I've recreated that one. Next is water, and that just translates straight down from here. So plus 2 water. Okay, I've done that one already. And then finally is sulfur, which just translates from here, plus 3 sulfur. Okay, so this side is done. Go back up to the top. I've got SO2, KOH, Cr2O3. SO2 and Cr2O3 already translate directly. And then look at that. Just like magic, there is a perfect number of potassium to combine with the perfect number of hydroxide to make 4 KOH for your final answer.